Hello everyone, my name is Kadir Gümüs and thank you all for watching this presentation. Today I will be presenting about end-to-end learning of geometrical shaping, maximizing generalized mutual information. A paper authored by me and co-authored by Alvarado, Chen, Christiam, Häger and Erik Agrell. In today's society, we want and need higher throughput for high-speed optical fiber networks. One key method of achieving this is by using signal shaping. Signal shaping itself can be split into two broad categories, probabilistic shaping and geometric shaping. I'm going to be focusing on geometric shaping during this presentation. What we want to achieve using geometric shaping is this black line over here, the capacity, the theoretical maximum. Standard constellations that we're using nowadays perform far from this capacity, with approximately a 2 decibel gap between the capacity and a PM8 constellation. Using geometrical shaping, we're trying to close this gap using methods such as set partitioning, APSK constellations, and polarization ring switching. And so far, we've been capable of closing the gap by about 0.7 dB. But if we want to close this gap even more, what we need are constellations of higher dimensionality, and therefore also higher cardinality, as the cardinality increases exponentially with the dimensionality. The problem is, such large and complex constellations are difficult to optimize, and our current methods are unscalable. However, recently machine learning has been gaining popularity for use in geometric shaping. But because this is still quite a recent advancement, we still don't know what types of networks are suitable for geometric shaping. The performance metric we use to determine the performance of a constellation is the achievable information rate. The achievable information rate represents the amount of bits a symbol can represent for safe transmission. We are specifically looking at the generalized mutual information, the GMI. The GMI is the achievable information rate for bit and delete code modulation systems. The GMI itself depends on several factors: the signal-to-noise ratio, the constellation size, the dimensionality of the constellation, the position of the constellation points, and the binary labeling. During geometrical shaping, we are trying to optimize a constellation of a particular dimensionality of a particular constellation size for a specific SNR by moving around the positions of the constellation points and the binary labeling. So our question is, how can we effectively perform geometric shaping using machine learning? And in our paper, we contributed this in several ways. First of all, we show that the GMI as a cost function is highly non-convex. We also show that generic machine learning methods are non-effective at reliably finding global optima. We also show that domain-specific knowledge is very important for the optimization. And finally, we propose a simple network for GMI-based geometrical shaping. The general structure used for geometrical shaping is the Autoencoder, as proposed by O'Shea et al. And used in other works such as Jones et al. And Karnov et al. The Autoencoder itself consists out of 3 different parts: the transmitter part, the channel part, and the receiver part. A sequence of bits B gets mapped to a one-hot vector. This one-hot vector represents a constellation point and is the input to the transmitter part of the network. This one-hot vector gets mapped to an output layer through several hidden layers. The output of the output layer is an n-dimensional vector that represents the position of a constellation point in n-dimensional space. This n-dimensional vector first gets normalized, and then it gets used as the input of the channel part of the system. This channel part of the system adds some noise to this n-dimensional vector, and as output you get a noisy vector. This noisy vector gets used as the input of the receiver part of the system. The receiver part of the system tries to learn the posteriors, and based on that, the GMI can be calculated. However, because we are focusing specifically on an AWGN channel, we know what the channel law is, and we can use exact posteriors to calculate the GMI, so a receiver part of the network is not necessarily required. To test the validity of such a method, we've decided to implement this network and decided to run the optimization 200 different times with a random initialization each time. Then we've decided to plot the end GMI of the constellations that we get at the end and see how it performs compared to several baselines. So the baselines we are using to compare it to are 16 QAM and a state-of-the-art constellation as proposed by Bin et al. And when we plot the PDF, we see that the distribution itself is very, very wide, indicating that the GMI is very non-convex as a cost function. We also see that most of the constellations perform worse than 16 QAM, and very rarely we get constellations that are as good as the state-of-the-art constellation. To show this a little bit more clearly, we've plotted the PDF as a cumulative distribution function over here. This blue line is the same line as this PDF, but then plotted as a CDF. And indeed, about 90% of the constellations end up with a GMI worse than 16 QAM. So to try to improve the performance, we've looked into several different methods. First of all, we've decided to use some machine learning methods, such as a cyclical learning rate. With a cyclical learning rate, what we're doing is that throughout optimization, we're changing the learning rate cyclically. And we do see a small improvement in performance, but it's still not sufficient, as over 80% of the constellations are still worse than 16 QAM. After that, we decided to look into more domain-specific knowledge, such as the binary switching algorithm. The binary switching algorithm is an algorithm that optimizes the binary labeling of a given constellation. So throughout optimization, once every few hundred iterations, we perform the binary switching algorithm. Once again, there is an improvement when compared to the baseline, but it's still not sufficient. Finally, we decided to look what would happen if we were to initialize the system with a good constellation, such as a 16 QAM constellation. And what we see here is indeed quite promising. The constellations we get are never worse than 16 QAM, which makes sense as that is the initial starting point. So we decided, because this was quite promising, we decided to implement this into our network. Or a network differs from this regular network in several ways. First of all, we use only one layer in our network. Because of this, the weights in the network directly corresponds to the position of the constellation points. So we're applying the gradient directly to the constellation points themselves, which is somewhat similar to the work proposed by Fushini et al. The second thing we decided to add was to initialize the network with a good constellation. Because we are optimizing specifically for an AWGN channel, we can calculate the GMI using Gauss-Hermite instead of using a Monte Carlo approximation. Because we are using Gauss-Hermite, we remove all of the stochasticity of the system, making this entire optimization purely deterministic. So the optimization needs to only be run once. Here we have an animation showing how our method goes to work. So on the left side of the figure, you've got a constellation plotted 6 different times, 1 time for each bit position. If a constellation point is blue, it means that it has a value of 0 at that particular bit position. If a constellation point is red, it means that it has a 1 at that bit position. On the right side of the animation, we've plotted the GMI compared to the amount of optimization iterations. So when we start the optimization, we see that as we move around the constellation points, the GMI increases significantly. At some point, this increase levels off because we are very close to the optimum in that case. And what we get as the end GMI is something that's quite good. So to test the actual validity of our method, we've decided to run this optimization for several different constellations of different dimensionalities and different constellation sizes for a different range of SNRs. So first of all, we have here a two-dimensional, we've decided to run the optimization for two-dimensional constellations of size 256. This black line over here is a Gray-labeled 256 QAM, the standard constellation. This blue line over here is a state-of-the-art constellation as proposed by Chen et al. This red line over here is the result of our optimization. As you can see, our optimization has a slight improvement when compared to the state-of-the-art methods, and significant improvement when compared to the regular QAM constellation, with about a 0.73 dB gain in SNR and a 17% added reach. The reach, by the way, is calculated using the GN model proposed by Pogiolini et al. So to see whether this method also works with very large constellations, we've also run the optimizations for two-dimensional constellations of size 1024. So what we have over here is the black line, which is Gray-labeled 1024 QAM. This blue line over here is a state-of-the-art constellation as proposed by Miller et al. And this red line over here is the result of our optimizations. And indeed, once again, there is a slight improvement compared to the state-of-the-art constellation, and a significant improvement when compared to 1054 QAM. Finally, we want to look whether or not our method also works for constellations of higher dimensionality, so we decided to run the optimization for four-dimensional constellations of size 64. The black line over here is a two-dimensional constellation, the PM8 QAM constellation. The blue line over here is a state-of-the-art constellation as proposed by Bin et al. And the red line over here is our proposed method. And indeed, even for higher dimensional constellations, we still get a significant gain compared to the standard constellation and a slight increase compared to state-of-the-art methods. So, what can we conclude from our work? First of all, a one-layer neural network is sufficient for GMI-based geometrical shaping. Second of all, because GMI-based geometrical shaping is a very non-convex problem, the initial starting constellation is of great importance. And finally, using our method, we can create state-of-the-art constellations. In the future, there are two specific things we want to look into. First of all, we want to perform the optimizations for larger constellations of higher dimensionality. And finally, we want to adapt our methods for non-linear channels. Thank you all for watching this presentation.